Hello, my name is John Chamberlain. Welcome to Fundamentals of Light and Laser with Course 1. Today we're going to look at Laboratory 1-3C, Windows and Mirrors. Part 1 is going to look at Fresnel reflections in an acrylic block. Okay, well let's look at the equipment we're going to be using in today's lab. Of course, we're going to be using a laser. This is the laser we've chosen to use, and it's mounted on a lab jack so that we can keep it stable and pointed in the right direction. We've got our photo detector and the power meter that we'll be using. We have another lab stand over here that is going to hold our acrylic block, and we have our beam block. Okay, so the first thing we need to do is go ahead and measure the power of our incident beam, and we've already got our power meter set up to do that, so let me just go ahead and take advantage of that setup, and you'll notice that our power meter is showing about 0.80 microwatts, and with our 1000 to 1 attenuator, that would imply that we have a power of 0.81 milliwatts. So I'm going to write that down in our data table. 0.81 milliwatts. And now we're ready to begin to look at some of our Fresnel reflections and transmittance going on in this lab. And let me point out some of the setup here. As I move the power meter out of the way, you'll notice let's look over here at the block. We have to be very careful how we handle this block. We have done a very careful job of cleaning the block surfaces front and back, and handling it only with a tissue or with finger cots. And as we have positioned the block, we have to tilt it up just ever so slightly. We've used a couple index cards to accomplish that for ourselves, such that the light, as it passes through the block and reflects off the back side, will reflect back over towards the laser. And you'll notice over here that we've taped a little white index card to the front surface of the laser, and you can see the two images of the reflections coming off of our acrylic block. We had to position our block far enough away from our laser so that we got enough separation here so that we would be able to turn our detector around and be able to resolve those two dots with our detector, and we'll do that here in just a moment. Back over here on this side, move our detector back behind the acrylic block and measure the transmitted beam intensity. And I can do that for you. Look at the power meter over there, and we'll see we have a power reading of about 70 microwatts, which we'll record on our data table as being 0.7 milliwatts as the transmitted power, 0.70 milliwatts. Okay, so we're trying to get this lined up just right on that first Fresnel reflection, and it looks like I've just about got it. It takes a little bit of finesse. You notice we've had to prop up our detector just a little bit because of the angle, but I think we finally got it. And if you look at the meter, we're showing 0.03 microwatts. So I'll record that on my data table. Okay, I think I've got the second Fresnel reflection lined up now, and I'm seeing actually about the same power level, 0.03 microwatts. So I'll write that on my data table. All right, now that we've collected all of our data, let's work through some of the math calculations. Starting with step 3 in our text, it asks you to calculate the approximate power absorbed by your acrylic block. To do that, you start with the incident power and subtract out the measurement of your transmitted power and the reflected power from the first face and the power reflected from the second face. And if you start with 0.81 milliwatts, subtract 0.7 milliwatts and 0.03 milliwatts and 0.03 milliwatts, you will come up with, in our case, we came up with 0.05 milliwatts. So that is our absorbed power in our block. Next, we're asked to calculate the value of that predicted value of what the reflected value would be from that first phase. To do that, we need to know what the R coefficient is. Start with the incident value of power of 0.81. And the R value is given in the text as the ratio of the index of refraction minus 1 squared over the index of refraction plus 1 squared. Okay, and the index of refraction for our plastic block is 1.49. And if you put that in here, this coefficient then becomes a value of 0.0387. And if you work the math out on that for our example, we end up with a predicted value for PR1 of 0.031 milliwatts. And that agrees very well with our observed value of 0.03. Since we only had 2 digits on our readout, that would exactly round to 0.03. So our predicted value agreed very well with our measured value. Next, we're asked to calculate the reflected power from the second phase. And that will be, we'll start with the power that comes from that first reflection, which would be the incident power minus the reflected power that we predicted should come from that first reflection, minus the power that was absorbed by the beam as it transmitted through the plastic, times those coefficients R times 1 minus R that we calculated up here. You'll come up with a value, in our case, of predicted value of 0.027 milliwatts, which again agrees very nicely with our observed value for P sub R2. We could only read 2 digits, so 0.03, and 0.027 would also round to 0.03. So we had a very good agreement there. Okay, and then lastly, we're asked to calculate the transmitted power, and that'll simply be the incident power minus the reflected 1 power minus the absorbed power through the block minus the reflected power from the second phase, and that's just simply a matter of substituting the values that we've calculated already, and that predicted value would be 0.702 milliwatts, which again agrees very, very well with our actual measured value of 0.70 down to the 2 digits that we can calculate or that we can measure with our meter. Procedure asks you to calculate a percent difference for those, and sure enough, as I pointed out, we've had excellent agreement, and you should see that we've got essentially 0% difference in our measurements. Hopefully your results will turn out just as well. The last thing this laboratory asks us to do is to solve for the absorption coefficient of the plastic material we used in this laboratory. And to do that, we'll use the formula given in your text for the absorption of the energy going through this plastic material. E is equal to E sub 0 times e to the minus ax. And we need to solve for that variable a. To do that, we would divide both sides by E sub 0 and have e to the minus ax like that. And then to isolate that exponent over there, we'd take the natural log of both sides. So we'd have natural log of e over e sub 0. And this will take the natural log of e to the minus ax would give us minus ax. And then to isolate just the a, we would divide both sides by negative x. So we'd have by minus 1 over x. Where x over this side would just leave us with A. So there's our expression for A. And then we just would substitute in the values for E and E0 and X. Our block measured to be 2.2 centimeters. So I would have negative 1 over 2.2 centimeters. And the natural log for us, our exiting after going through 2.2 centimeters, our power was 0.70 milliwatts. And the incident power was 0.81 milliwatts. And after we put that into our calculations, we end up with a value of 0.066 per centimeter is our absorption coefficient. So your material may differ, but that's how you would go through that calculation to determine the absorption coefficient for your plastic material. So that concludes the first part of Lab 1-3C. Now we're ready for Part 2 of Lab 1-3C, where we'll be dealing with the mirrors portion of the lab. Let's look at the equipment. We still have our laser on the lab stand and our power meter with the detector already set up to record the power level of the incident beam. Looks like we're reading about 0.77 microwatts, which with our attenuator there, we're reading about 0.77 milliwatts. And we have we've positioned two mirrors. We have our front surface mirror that is positioned into our beam steering assembly from our Newport kit. And we also have a rear surface mirror ready to go. And it is also positioned into our modified target assembly. And we'll see how that will play in just a moment. So we've got our incident power at 0.77 milliwatts. We record that. And now let's remove the power detector, and we'll see the reflected beam is coming back here. And now we need to position our detector and record the power that's coming into there. Okay, I think I've got it lined up pretty good now. Looks like we're measuring 0.74 microwatts, which with the attenuator comes out to 0.74 milliwatts. That's what I've written on the board here, and if we do that calculation, it'll come down to 0.961 for the reflectivity of the coating for this front surface mirror. That's a pretty good mirror. All right, so now we're ready to switch to the rear surface mirror. So let me make that switch. Okay, now that we've got this rear surface mirror set up, and I've got it all lined up very nicely, and the power meter is lined up, and if you look, the power meter is reading 0.65 microwatts. With our attenuator, that tells me that we're reading 0.65 milliwatts. Let me remove the power detector for you, the photo detector, and we'll look at that image of that reflected beam. And you'll notice that we can scarcely see the second beam image. So really what we're measuring is the power from reflected beam 1 and reflected beam 2 together. So I'm going to have to record that on my data table as the power of R1 and R2. We're not going to be able to separate those two. So I'm going to write that down as 0.65 milliwatts. All right, the last thing we need to do to finish this lab is to measure the amount of laser beam that is transmitted through this rear surface mirror. It may not look like there's anything going through that mirror, but if you dim the lights, in fact, you can see a small part of the beam going through. So we're going to position the photo detector over here behind the rear surface mirror, lower the lights, and do our best to try to take a reading. Now we've got the beam going through the rear surface mirror, into the photodetector, and you'll notice we have removed the 1000 to 1 attenuator because we've got a very low power beam that's being transmitted. And we've also rescaled the power meter to show milliwatts directly, and it is reading 0.01 milliwatts. Okay, so let's make the calculations for this laboratory. First, let's review our data. For the incident power, we measured 0.77 milliwatts. For the reflected power, we measured 0.65 milliwatts for the combined two beams that were reflected from the two surfaces. And the transmitted power that went through that rear surface mirror, we measured 0.01 milliwatts. Now, theoretically, the power that should have been reflected from that first surface is equal to the incident power times the reflectance from that front surface, which is the incident power times 1 minus the index of refraction squared divided by 1 plus the index of refraction squared. And using the crown glass index of refraction of 1.52, it will come up with the incident power was 0.77 milliwatts, and the reflectance will be 0.0426. That's if you substitute crown glass into this formula here. And the result will be that you should see 0.033 milliwatts of power coming out of that first reflection. Okay, we had a little bit more than that coming out of both of them. We don't know how much came out of just the first one. The reflection coming out of the second reflection will be the incident power minus the power reflected from the first one that we calculated from up there times the reflection from that reflectance of that coating, which we measured up here on our first one. We'll use that reflectance, which will be 0.961 times 1 minus the reflectance of the back surface of that crown glass, which we just calculated here to be 0.0426. So if we put those numbers in here in this equation and substitute that in, the reflection power from the second surface should have come out to be 0.678 milliwatts, if you'll calculate that. So now if you calculate what's left over, the transmitted power would be the incident power minus what was reflected from the first surface minus what was reflected from the second surface. And if you substitute those values in, you should see that we should get the result of 0.059 milliwatts. Now, we didn't have exactly that, and so we should calculate a percent difference for each of those. For example, for the reflectance from the first and second surfaces, we'll just have to combine those because we can't separate out that. So let's just look at the combined totals. The percent difference for the combined total of the reflectance, for example, for our situation, we'll say we measured 0.65 milliwatts, and we predicted that we should have about 0.68 and 0.3, which would be about 0.71 milliwatts. And if we calculate the percent difference from that, then you'll see that we'll get about 8.5% difference. So that's not too bad. We're less than 10% error measure on that. That's a pretty good result. However, the transmitted power, we're quite a bit farther off than on that. And if we do that similar calculation on that, you'll see that we're about 80% off on that one. So our mirror was not transmitting very much power as much as the formula would have predicted. So anyway, your results will vary. Your mileage may vary, but you'll see how to do that now after watching this video. And that'll conclude Lab 1-3C for this lab, and we'll see you again for the next laboratory activity. you.